Hello, my name is Adam Sawicki. I work as a developer technology engineer at AMD. In this video, I would like to talk about GPU crashes and present you our new tool that can help in capture and analysis of those crashes, Radeon GPU Detective. The agenda of my presentation looks like this. We will start by talking about GPU crashes, what are their possible causes, what are the effects we observe, why are they difficult to debug, why they happen so often, and what are the existing solutions to debugging them. Then I will present Radeon GPU Detective, the workflow of using it, and we will go step by step through the crash analysis report that it generates. Let's say we focus on programming using graphics APIs like DirectX 12 and Vulkan. Any text marked in green in this presentation is about DX12 and anything in red is about Vulkan, but they are both very similar. And by the informal term GPU crash, I mean what is really called timeout detection and recovery, or TDR for short. It's a mechanism in modern Windows that detects GPU failures and restarts it. It was introduced first in Windows Vista, in the new display driver model. Before that, a GPU crash resulted in a crash or hang of the entire machine. Now, only the game crashes, while the rest of the system, including our development environment, continues to work just fine, which is a great help in debugging. The list of possible causes of GPU crashes starts from a bug in our application. By this, I mean incorrect use of the graphics API function calls. This is the most frequent cause. Bugs in the graphics driver also happen and can cause a crash. Finally, there might be some external factors, like user updating graphics driver while the game is running, or even some hardware failure. Let's focus on the application bugs. What can go wrong? The most canonical example would be an infinite loop in a shader. After all, we talk about timeout detection and recovery here. Shaders are not like CPU programs that can run for hours. A single draw call or compute dispatch should take microseconds or at most milliseconds. If it doesn't complete within seconds, the system assumes that the GPU hung. It may be caused by an oversized dispatch, reaching out to system memory too often, which is pretty slow, or too many commands in the command buffer. Then, memory page faults are also possible. GPUs also have virtual memory addresses, and using an incorrect address is a critical error. It happens most often when we try to use in our shader a buffer or a texture that has been released or evicted from GPU memory. Possibly also when we go out of bounds with some indexing or address calculation. Incorrect resource bindings also happen quite often with outdated resources bound to shaders through descriptors. Finally, some corrupted data in memory can also cause a crash. For example, inside a buffer holding acceleration structure for ray tracing. Other causes are also possible. Why do those crashes happen so often? First of all, the old graphics APIs like OpenGL, DirectX 9 or 11, most of the functions return some error code. Driver is expected to validate everything. Then, GPU crash is usually a driver bug. On the other hand, in the new APIs like DirectX 12 and Vulkan, driver is expected to be thin and simple and not to do too much validation. Thanks to this, it can run faster. Many API functions just return void, but the consequence is that we can easily misuse the API, which is an undefined behavior and can lead to a crash. In the new APIs, some functions still return an error code, especially those that allocate some memory, because these can obviously fail due to an out-of-memory error. But most of the functions, those recording commands into a command buffer, just return void. And yes, there are some debug layers that we can enable for additional validation, but more on this later. Normally, driver is simpler and faster and doesn't do too much validation, but it also makes it easy to misuse the API and cause an undefined behavior, which can easily lead to a crash. Driver bugs still exist and can cause a crash, but it shouldn't be your first thought. Crashes also happen more often because these days we seem to be heading more and more towards more free-form use of some pointers or addresses. In the old APIs, we had to create a separate objects for any vertex, index, or constant buffers. Today, in DX12, we have a type holding just a virtual memory address to a buffer that we can freely shift left and right. And the more we use things like bindless, dynamic indexing, indirect calls, ray tracing, etc., the more we use some freeform pointers, which are a frequent source of crashes. I previously said undefined behavior. This is a broad term that can really mean anything. In graphics programming, it can mean a whole spectrum of effects, starting from the game working just fine and doing what we want, through some graphical corruptions, artifacts on the screen, to the entire game crashing. Please note that what works on one GPU may not work on another one, coming from different vendor, for example AMD versus NVIDIA, or a different architecture and model, for example Radeon 6000 versus 7000 series card, or even depending on the version of the graphics driver or the operating system. If something works on one type of GPU and doesn't work on another one, it is still likely a game bug and not a driver bug. When the thing that we call GPU crash actually happens, the effect on modern Windows is that the GPU and the driver is restarted. From the perspective of our code, it means that some function of the graphics API, very often present, returns a special error code, like device lost or device hung. Blue screen of death or a hang of the entire machine does happen sometimes, but is less frequent these days. This is a photo I took when I once had this interesting crash that looks like half blue screen and half corruption. When I set an API function returning an error code, it has two important implications. First, it doesn't mean our C++ code, our CPU code is crashing. It actually continues. Theoretically, we could even restart the renderer part of the game code, reload all the assets, and continue gameplay. Of course, no one does that. No one implements such a recovery code in a game, but we can at least save some log or some dump to a file, send it to some server, and then terminate soon after. This is why we call it a crash. Second implication is that an error code returned from a function like present means we have it at the level of the entire render frame. It doesn't tell us which specific render pass, which draw call, which shader caused the crash. And this is a big problem. This entire presentation is about trying to solve this problem. But first, let me explain why is it so difficult to debug. First of all, what I call here an informal GPU crash can really mean different things under the hood, on the driver or the hardware level. It can be, for example, a timeout due to an infinite loop in a shader. It may be a memory page fault, some piece of GPU hanging, and possible other things. Modern GPUs are complex. They work asynchronously as a coprocessor executing commands at their own pace while the CPU already calculates the next frame. They are heavily pipelined, which means you have multiple commands in flight at the same or different stages of the graphics pipeline, and each one goes through many stages. And the GPUs are heavily parallel. There are many threads, meaning many pixels, many vertices processed at once. Finally, even if one hardware block fails, others may continue. There is no global stop and break into a debugger like we do with our CPU code. What are the existing solutions for debugging GPU crashes? Can we make a capture with Pix or RenderDoc? Not exactly. Those tools provide great help in debugging various problems, but they need a successfully rendered frame to capture, and we usually don't know which frame exactly will crash. There are debug layers that we can enable in the API to validate the correct use of the graphics API, and they provide great help. They have moderate performance overhead, and we should all use them during development. One caveat though is that they can only validate things that are known to the CPU timeline, like the parameters passed to the API calls, command buffer submissions, or resource allocations. They cannot validate what is only known on the GPU timeline or in GPU memory, including descriptors. And then we have the GPU-based validation that we can enable for additional checks that happen on the GPU by instrumenting shaders. But This mechanism has such a high performance overhead that it usually makes the game unplayable. We might need to wait minutes, if not hours, to launch the game, compile all the shaders, and render any single frame. To continue our list of possible solutions, as the last resort, you may try to debug by disabling various parts of the game and checking if the crash goes away. Start from lowering the mine quality preset from ultra to high, medium, low, etc. Disable any ray traced effects, as they are a frequent source of crashes. Try to lower GPU memory usage, for example, by selecting lower texture quality to eliminate the possibility that the crash happens due to out of memory. Finally, if nothing helps, modify the game code or shader code to disable individual passes and effects, simplify some shaders, for example, by replacing them with outputting a constant color, something like that, to see if the crash goes away. This may help you to identify the culprit pass and shader. There is also a debugging method commonly called breadcrumb markers that you can implement yourself. The idea is to create a buffer for numbers that we will write between draw calls. I will describe it briefly in a second. There is also a standard part of DX12 called Dread that would implement such breadcrumb markers automatically for us. And finally, there are vendor-specific tools. You know what I mean. NVIDIA provides Aftermath, and we provide Radeon GPU Detective. The idea of breadcrumb markers is to create a buffer in the system memory that will be available to the GPU and have it persistently mapped. Then, during rendering, we write a single number between draw calls to indicate the place in the frame where we are. Finally, after the crash happens, we inspect the mapped pointer to see the value, and from that we can hopefully find out which command was successfully completed last. Those breadcrumbs look good on paper, but they are not always reliable. They may give the correct information about what caused the crash, but please take those results with a grain of salt, and also please test multiple times to see if the results are consistent and not all over the frame. The reason those may not be very reliable is because, well, even if those breadcrumbs do what the API says, they write a value to a buffer between a draw call starts or after it ends. But on one hand, it may happen that the GPU doesn't stop on the first failure. It may continue executing next draw calls, even entire render frames. So we may see our markers too late. On the other hand, if the GPU stops, it may have some caches not flushed. So we may see the markers too early. Now let's talk about Radeon GPU Detective. Radeon GPU Detective, or RGD for short, is our new member of the Radeon Developer Tool Suite. Together with the existing tools you may already know, Radeon GPU Profiler, Radeon Memory Visualizer, Radeon GPU Analyzer, or Radeon Ray Tracing Analyzer. It is a tool for post-mortem analysis of GPU crashes, which means that you need to set the driver to the special crash analysis mode before reproducing the crash. After it happens, a crash dump file or RGD file is created. That's a new file format that we defined, and from this we produce a concise crash analysis report in text or JSON format that can help to narrow down the search for the crash root cause. Here are the requirements of RGD. We support Windows 10 and 11 and the last two generations of our graphics cards, Radeon 7000 and Radeon 6000 series GPUs. It requires a driver version at least from the December last year, and the graphics APIs supported are DirectX 12 and Vulkan. Let us take a quick look at the workflow. How to use RGD in practice. We start with Radeon Developer Panel, which is the entry point for using all our tools from the Radeon Developer Tool Suite. So we start by launching RDP and clicking Connect button. We then select Crash Analysis as our workflow. API can be set to Workflow Supported, which means to automatically detect the API. We can also set it to explicitly DX12 or Vulkan. While Radeon Developer Panel is running in the background, we can launch the crashing application. RDP process detects the newly launched app, and from the app startup, the tool is tracking all the memory transactions and command submissions. Once the application crashes, all the tracked information is written to a binary crash dump file or an RGD file for further analysis of the crash. That file is a binary format that contains all the information that is captured or tracked by the tool. We will see how this information is presented by the RGD tool and can help a developer debug the crash and find the culprits. When the RGD crash dump file is generated, a report in text format also gets auto-generated using the RGD command line tool. This happens under the hood, launched by Radeon Developer Panel, but we can also use the RGD command line tool manually to generate a report in a machine-readable JSON format, or to include additional details by passing extra command line parameters. When the crash happens, a new crash dump appears on the list of recently collected crash dumps. You can double-click on it or right-click and select Open Text Summary from the context menu. Then a text file opens with the crash report. Please note that there is no need to modify your game code to integrate RGD support. There is also no new UI window to learn to navigate. All you see as the result of RGD working is this text file with the report. The report contains 4 sections. Let's go through them one by one. As I mentioned before, the tool keeps track of completion status of all the commands. These commands include execution markers, which are presented in execution marker tree and markers in progress section. In case when a crash was caused by a page fault summary section describes the virtual address which caused the page fault, and in the summary output it is denoted as an offending virtual address. Then all the resources associated with the offending address is provided to help finding out the culprit resource. System info section provides detailed information about the system on which the crash was produced. The execution marker tree contains a list of command buffers that were in progress when the crash happened. For each command buffer, it presents a hierarchy of user markers and driver markers, indicating draw calls, dispatches, and entire render passes that were not started yet, in progress, or completed at the moment the crash happened. Only the in-progress markers are expanded to make the tree shorter and easier to inspect. Here on this picture, we can see that some markers are wrapped in double quotes, and these are user markers, or the markers added by the developer. Without them, we would see here only a flat list of draw calls and compute dispatches. It is worth surrounding them with a hierarchy of user marker strings denoting render passes to provide the logical structure of the render frame. To provide custom markers in DX12, unfortunately PIX markers don't work, so we need to use special markers provided by the IGS library or the replacement header for PIX markers. But chances are that you have them already integrated because these are the same as for RGP. In Vulkan, it is enough to use the standard debug utils extension and the begin label end label function. Unreal Engine also has them integrated already, so just enable the console variable shown here. We put a lot of effort in designing the output file so it is the most concise and includes the most relevant information for analyzing the crash. The markers in progress section helps you in a glance see only the markers which were in progress at the time the crash happened. Obviously, these are the markers you are going to be most interested in. As you can see on this slide, the hierarchy is noted by the / character, similar to what we see for folder paths in file system. And we even squash the repeating occurrences for you. If you need extra context, you can always refer to the execution marker tree. As I explained before, there are various kinds of GPU crashes. If it was not a page fault, it likely means it was some hang. It could be, for example, an infinite loop in a shader or some draw code just taking too long. But if it was a page fault, the report will have an offending virtual address printed and a list of all resources, buffers and textures that ever existed in memory overlapping with this address. The list of associated resources printed for the offending virtual address is tracked since the launch of the crashing application and is not limited to the moment when the crash happened. This is important because the app may try to access the resource that has been already destroyed or evicted from memory, which results in the crash. We show many parameters of the resource. For example, for textures, we show texture dimensions, pixel format, flags, etc. They can help to identify which resource was that. Just like with execution markers, resources also have string names assigned. This of course requires modification of the game code, but it is worth assigning your resources some meaningful names because it can help to identify which resource was that even better. To do that, in DX12 you can use the standard setName function. And in Vulkan, once again, you can use the standard debug-utils extension. The resource timeline section includes a list of explicit events, such as create and destroy, and other events made by the driver, such as bind and make resident, basically all the events that occurred throughout the resource's lifetime. Timestamp format is hours, minutes, seconds, and clock cycles, and it shows the duration from the application launch. Now, let's look at how to interpret those results. This resource, named post-processing render target 4, is identified as an associated resource with the offending virtual address, and the resource timeline shows it was destroyed at 9 seconds timestamp. So, the application was trying to access a resource which is already destroyed, which resulted in a crash. So we can conclude that very likely the bug is about trying to access this specific resource after it was destroyed, the popular use after free bug. Over the past year, we analyzed hundreds of crashes, and looking at their crash analysis reports, we could group them by three main categories, depending on the answer on two main questions. Was the page fault detected? And were any resources associated with the offending virtual address printed? Let's look at those three cases. If page fault was detected and there are some resources printed associated with the offending virtual address, it likely means the crash was about trying to access one of those resources after it has been evicted or destroyed. If there is a page fault detected, but there are no resources under the offending virtual address, it can mean an out-of-bound access to memory. Finally, if there is no page fault detected, it likely means it was a hang, some kind of, like for example, an infinite loop in a shader or just some GPU workload taking too long time. Use execution marker tree to narrow down which render passes and draw calls were in progress during the crash. Finally, at the very top of the report, we also include basic information about the hardware-software environment where the crash happened, including the installed CPU, GPU, the amount of system memory, video memory, host name, full path of the application that have crashed, its process ID, and other parameters. This is a great help for developers who want to track the system configuration where the crash happened and they want to reproduce the crash maybe in the same environment, or they have to handle multiple crash reports from across many different machines. To summarize, the way RGD works under the hood is that Radeon Developer Panel, together with our driver, captures the crash and creates an RGD file, which is a binary crash dump. Then, when you double-click on the crash dump in the panel, it automatically launches RGD command line application that converts this binary file into a text report. You can also launch this application manually, and there are additional command line parameters available. You can use JSON output format, which may be good for automated processing to make RGD part of your crash reporting pipeline. RGD application is open source, with the source code available on GitHub. So you can inspect the code and you can also report any bugs, any feature requests or other comments as issues or pull requests in this repository, or just contact us if you have any feedback. We will develop it further. To conclude, with Radeon GPU Detective we can capture and analyze GPU crash dumps on the PC with AMD GPU. The tool is easy to use. If you implement crash reporting with Dread, its output may also become more reliable by just enabling crash analysis, but using RGD crash reports gives you more information about the details of memory resources and their timeline when they were destroyed. RGD has very low performance overhead. It is not intended to be used on players' machines or during performance profiling, but it can be used during development and testing, and the game should be still perfectly playable. Finally, I want to thank all the people mentioned here for their help and involvement in this project. And I invite you to visit our website gpuopen.com and our social media. Thank you.